Swayam Prabha. Digital India. Educated India.
So now in the last lecture, we were looking at the aldol reaction of a ketone with itself. So the example that we can basically look at is acetaldehyde reacting with itself to give you a new product, which would be the aldol as shown here, right? And so the important point here to note is the connection that is being made between this 2, 3, 4 and 5. So the bond that we are looking at is this carbon-carbon bond between carbon 3 and carbon 4. Okay, so that's why it's this is pretty straightforward in our understanding. But now in this lecture, what we will look at is the concept of cross condensations. That is, so here what you have seen is that partner A basically reacts with itself. So an aldehyde reacts with itself to give you the aldol product. Okay. Now what if we have A and B? All right. And can we do aldol reactions with this? So these are known as cross condensation reactions. And in this lecture, we will look at some examples of this. Okay, so now, let's take a simple example here. Now I'm just going to start with something like acetophenone, basically. All right. So now if I take acetophenone, so if I look at this ketone here, we will straight away see that the enolate can be formed over here. But the enolate, sort of is not possible in this position, correct? So therefore this has one enolizable hydrogen. Okay, now of course, as we know, it can react with itself and give you the aldol product, but you can also react it with an electrophile that is more reactive. So for example, such as this. Okay, so let's say we start with this 4-nitrobenzaldehyde, and I just want to point out here that this hydrogen, this is an aldehydic hydrogen, and so this is also not enolizable, and clearly there is no hydrogen here to enolize. Okay, so therefore when I mix these two reagents together, the only enolizable hydrogen in the presence of a base is this. Okay, so what we can expect as the first intermediate in the reaction is this enolate, right? And the coupling partner or the electrophile that is shown here is this. And now when the reaction actually happens, you can see that this enolate reacts in the following manner. It goes, attacks the carbonyl, and now the carbonyl can open up. Okay, and so again, just to be consistent, let's keep the same numbering sequence. So this is 1, 2, 3, 4 and 5. Okay, so I'm just going to draw this once again in the next page, in a fresh page, so that we understand this better. So the enolate we are looking at is this, and the aldehyde that we are going to react it with is this. Okay, so we'll very soon discuss few aspects of this reaction, but you can clearly see here that, for example, that the aldehyde is quite reactive in this case, and therefore the reaction goes forward. All right, so let's look at the numbering again. So this is 1, 2, 3, 4 and 5. Okay, so I'm just going to call this as pH, and so this becomes pH CO. This ketone is restored, and now there's a new bond between this and this. So I'm just going to draw this in a different color so that you can clearly see it. This is O minus, and this is 4 nitro phenyl, and this is hydrogen. Okay, so this is the kind of reaction that can occur. Now the question here, again, let me just complete the numbering so that we can go forward with this reaction. 1, 2, 3, 4 and 5. Okay, so now you can propose a reaction. This aldol product can pick up a proton, and so the proton that you can pick up is shown here. So C double bond O, OH. Okay, so you still have some base floating around in the reaction, so you can propose that this can form the enolate, O minus, OH, and the remaining structure remains the same, right? So this is the enolate, and this is the enolizable hydrogen, and so it can form the enolate. And we've already discussed this in the previous lecture, that you can have what is known as the E1CB reaction, which is the E1 conjugate base reaction, where this comes in here, this goes here, and you can kick out the hydroxide ion. Okay, so the final product that you would get in this case would be C double bond O, NO2. Okay, so now the yields are pretty good in this reaction. I don't have a number here, but usually you get this in excess of 80%. So now the question here is, why doesn't the ketone react with itself? Okay, so this ketone that is shown here, CH3, of course it can react with itself. That is, this enolate that is formed can react with the ketone. But we know that between aldehydes and ketones, aldehydes are clearly better electrophiles. And also notice in the example that we have shown here, we have taken a substrate reactant that is extremely reactive. So you also have a strong electron withdrawing group over here, the nitro group. So that is just going to pull electrons from this carbonyl, and it's going to make this center even more reactive. Okay, so the enolate, once it is produced, has a choice of reacting with this ketone, or it can react with this aldehyde. And between the two systems, we already know very well that the aldehyde is substantially more reactive, and so this is going to result in the formation of the cross condensation product. Okay, so this is one way in which we can do cross condensations. Let me just quickly write out another example, and then we can move on to the next topic, or summarize this topic. So the next example that I'm going to look at is pH C double bond O pH plus acetaldehyde. Okay, and so if you imagine, this has got two different partners. So here there's no enolizable hydrogen, there's no enolizable hydrogen. So the aldehyde is also not enolizable. Only this is enolizable. So the first step is fairly straightforward, which is that you produce this enolate. All right. Now what you can propose is that this enolate attacks here and produces this product. And so the product that you can expect would be okay. So let me just do the numbering once again. This is 1, this is 2, this is 3, this is carbon number 4, and this is carbon number 5. So let me just reiterate that: 1, 2, 3, 4, 5. Okay. So, by extending the logic further, the product that we would get would be pH. Once it undergoes the E1CB reaction, you will get this as the product, right? So this is a fairly straightforward argument, except that this is not the product that is formed. So what happens is actually that acetaldehyde reacts with itself, right? And it gives you the self aldol product. So this is the reaction that would occur, and you actually get the self aldol product. Okay. Now, what is the rationale for this? The rationale for this is that once an enolate is produced, the enolate reacts with the most reactive electrophile, and between the aldehyde here and the ketone, which is pH C double bond O pH, between these two, the aldehyde is clearly more reactive, and so when given a choice, the enolate is going to react with itself and give you the product, right? So therefore, in order to sort of generalize this concept, what we need to understand is the following. So in order for cross aldol to occur, what we would need is, point number one would be one partner only enolizes, right? So this is obvious because if you have both partners enolizing, then you have a problem of generating multiple enolates. And number 2 point would be that the other partner must be more reactive. Okay, so what we mean by this is that if the ketone is being enolized, then the other partner should be more reactive, in which case it must be likely be an aldehyde or a ketone with an electron withdrawing group or something that favors the formation of the cross aldol product. Otherwise, you would get self-condensation as the major product. Okay, so next we will look at some further aldol reactions. Okay, so now let's look at another important aldehyde that we have all encountered previously, which is basically formaldehyde. So formaldehyde is basically nothing but a carbonyl flanked by 2 hydrogens. So when I react this with acetaldehyde, for example, in the presence of a base, now what we would expect here clearly is that, again, I know once we have cross aldol reaction such as this, or a potential cross aldol reaction such as this, we need to look for enolizable hydrogens. So this hydrogen is not enolizable, this hydrogen is not enolizable. So this aldehydic hydrogen is also not enolizable. So the only enolizable hydrogen here is this in the acetaldehyde. Okay, so now let's say that this undergoes enolization and it forms this enolate. Okay, so far there's nothing major to discuss. Okay, now once this enolate is produced, this enolate can now react, and we know that between formaldehyde and acetaldehyde is more reactive, and so you're going to end up attacking here and producing this aldol product. Okay, so let me just draw out this product here so that you understand the chemistry. So I'm just going to flip this carbon to the other side just so that it's easy for us to understand this. Now this is the aldehyde, so this is 1, 2, 3, and this is carbon number 4 and oxygen is number 5. Okay, so we keep the same numbering, 1, 2, 3, and here is the formaldehyde part, which is number 4 and number 5. Okay, so this is 4 and this is 5. So far there's no problem, and you have a hydrogen here and a hydrogen here. All right, so under normal circumstances what you would expect is that this is going to give you the aldol product, right? However, since it's difficult for us to control the amount of base that is added in these reactions, you also have the possibility of the second enolate that can be formed, and so that enolate that is going to be produced, I'm just going to draw it out separately in the next page. And so this enolate is derived from acetaldehyde. So you have this OH, and this is the enolate. This is the enolizable hydrogen, and in the presence of the base, you could form O minus and hydrogen over here. So this again we have already looked at previously. Now the only situation here is that under normal circumstances, this would undergo E1CB reaction and give you the product. But since formaldehyde is so reactive in this case that it actually promotes the second addition in this situation. So what happens is that you get this, and the product that is formed is this C double bond O. This OH is already here. Now there is a second addition of a alcohol, or of a CH2OH. Okay. So again, just to keep the numbering consistent, so this is 1, 2, 3, 4, and this was for the previous addition. Now for this addition, this is 1, 2, and 3, and this would be 4, and this would be 5. So this is the bond between carbon 3 and carbon 4, and this would be carbon 5. Okay, so I'm just skipping the step of undergoing protonation, but you would first form the O minus alkoxide, which is then going to pick up a proton. So subsequently, this can happen once again, and the product that you can expect is this H, OH, OH, and OH. Okay, so again, keep in mind that formaldehyde is quite reactive, and therefore, this kind of a reaction is actually favored. Now, the twist in the tail is that what we would expect as the product is this OH, 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 but actually the product that is isolated is this OH, 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 and OH. Okay, so now this is the product, but you get this in between 80 and 90% yield. All right, so that's quite a large yield of the reaction. So what is going on? So what is going on here is that, just to understand here, these three CH2OHs are also preserved here, and one of these aldehyde is now undergoing reduction to form the alcohol. Okay, so I think many of you would be very familiar with this reaction known as the Cannizzaro reaction. I think you must have studied this in your 11th or 12th, but this is the reaction that we are familiar with aldehydes. So when you have an aldehyde, RCHO, and what can happen is that you have the O minus OH in the presence of a base, you get addition of hydroxide ion to give you this kind of a product, and now subsequently this can again lose another, this OH hydroxyl group can be deprotonated and you can get this dianion. Okay, now this dianion, again, so what I neglected to mention is that this R is actually non-enolizable, so therefore the addition to the aldehyde is the only reaction that can occur. Okay, but this tetrahedral intermediate that is produced is very reactive, and so when it collapses, what can happen is that obviously it cannot kick out O2 minus, but instead it can actually kick out hydride. Okay, so when this hydride is kicked out, it actually, what it does is, it doesn't leave as hydride, but it leaves as a hydride that attacks an aldehyde. Okay, so this is the H minus that is going to leave, and so the product that you're going to get from the first part now is RC double bond O minus, and the product that you get from the reaction with this would be RCH2OH. Okay, so you can go back and work out the mechanism of this reaction, but so what essentially happens is that with a non-enolizable compound such as formaldehyde, what you expect is that you get this kind of a reaction where you form this tetrahedral intermediate, and then there is a migration of hydride to the original aldehyde that is formed, and you get a mixture of the carboxylate as well as the alcohol. So therefore, this is not a reduction reaction, but actually it is a neutral reaction. It's a redox neutral reaction because the aldehyde is now oxidized to the carboxylate or reduced to the alcohol. So you get equal amounts of the carboxylate as well as the alcohol. So therefore it is not a reduction or an oxidation reaction. It is a redox neutral reaction. So now with this background, let us now look at the structure that we drew out in the previous example. So I'm just drawing it in a slightly different way so that we understand it better. So here is the OH, and the OH, and here is your aldehyde. Alright, and what can happen is that your formaldehyde produces this kind of an intermediate, and I just described to you how this kind of an intermediate can be formed, basically from formaldehyde, in the presence of addition of hydroxide ion, and subsequent deprotonation will give you this product. Now carefully see the arrow pushing. So what happens is this goes here, and this hydride goes over here, and this aldehyde opens up. And so the product that you get is OH, CH2OH, and this hydride is now forming a bond with this carbonyl. And so I'm just going to draw it out in a slightly different color so that we can understand it. So this is the hydride that has come out, and this is the OH. Okay, so I'm just going to highlight this. Alright, so this is just the hydride that is added over here. There's already a hydrogen present. So this is the product which is called pentaerythritol, which is actually produced in this reaction. Now let us now complete the other side of this reaction, and if you see here, the product that is formed is formate. Okay, so when you react acetaldehyde with formaldehyde, the aldol reaction does occur, but it subsequently goes forward and gives you the pentaerythritol as the product. So one of the messages that we can take from this reaction is that formaldehyde is an extremely reactive partner and is not really suitable for aldol reactions if you want to produce the aldol. Let's now look at, so is it impossible to use formaldehyde or to add formaldehyde? And the answer is no. So what we need to do is we need to modify the conditions a little bit, and now let's look at those modified conditions. Okay, so I'm just going to start with cyclohexanone as the starting material. So instead of using the formaldehyde as the electrophile, what we're going to do is we're going to use formaldehyde, but we're going to use dimethylamine, and we're going to use some catalytic amount of acid. Okay, so under these conditions, now let's look at what reaction can actually happen. So again, in the presence of catalytic hydrogen and dimethylamine, formaldehyde is going to produce C double bond N Me2 plus. Okay, so this is something that we have already looked at in the past. That is, if you take a aldehyde and react it with a secondary amine, you get an imine. Now this imine is the active electrophile that is produced. And we also, under acidic conditions, you can also imagine that the cyclohexanone will form the enol as shown here. And now the enol is the reactive partner in the proposed aldol reaction, and you get this kind of a reaction. So the product of this reaction, I'm just going to draw it out in the next page. So the reacting partners are the enol from cyclohexanone, which you already know the reaction mechanism to, and you have NMe2HH plus. Okay, so now the reaction that you're going to look at is this. I'm going to form here and kick this out. All right, so the product that is going to be formed is C double bond O. Okay, now let me just number this so that we can all be on the same page. So this is 1, 2, 3, 4, 5. Okay, so again here 1, 2, and now there's a bond between carbon 3 and carbon 4, and there is NMe2, and there used to be a positive charge, but that positive charge is now disappeared. Okay, so this is 3 and this is 4 and this is 5. Okay, so the product that is formed is actually the aldol type product, where instead of the alcohol you have NMe2. Okay, now in order for us to produce the alpha beta unsaturated ketone, what we can do is do a simple addition of methyl iodide in the presence of a amine base, and what you get is the product as shown here, which is C double bond O, N, Me, Me, Me. So you get this quaternary ammonium salt, and what we can expect is this quaternary ammonium salt is actually quite a good leaving group, and so since you have added a small amount of base, you may consider the formation of the enolate and NMe3 plus, and this enolate can now rearrange and kick out trimethylamine and give you the final product, which would be C double bond O. So this reaction can indeed occur, and what we'll do is we will start the next part of this lecture with this and move forward.